All right, so what we're focusing on here is just an introduction to limits. You may remember some things from limits from last year, you may not, but that's okay, because the bottom line is limits are not that difficult. Especially the limit problems that we're going to be addressing today. So something that you can kind of think about logically is, let's say that I am walking and every step I'm going to cut the distance between me and that stool in half. So I could take one step and I'm right here, and I could take another step and I'm right here, another step, I'm right there. I'm going to continue this process, getting closer and closer, obviously, to actually touching the stool, but I'm never actually going to get there. I'm always cutting that distance in half, but I'm getting closer and closer. So what we could do is we could talk about what am I trending towards? What am I approaching? If I were to carry this process on for infinity, where would I end up? Would I end up on the other side of the hallway? No, I'm getting closer and closer, a smaller distance each time. I'm actually approaching the stool. So if we kind of think about that, that's the limit. That's the limiting position. That's what I'm getting closer and closer towards. And that's what we're going to be talking about today. And we're going to evaluate limit problems graphically and then also numerically. And by numerically, I mean with a table. All right. So let's go ahead and look at a problem here. We'll what was that? Good marker. Here we go. We're going to explore a graph, and we'll use it over there here in a second. So we're going to explore f of x equals x cubed minus 1 over x minus 1. Let's just see what that looks like. Well, I guess we'll think about it first. So if you remember from pre-calculus and for algebra 2, you could plug in some different values. You might be able to plug in 0. So 0 cubed minus 1 over 0 minus 1. So that would be 0 minus 1, so negative 1, so that would be 1. So what that means is we could write f of 0 equals 1. So that's our x value. That's our y value. That would mean that on the graph we would have the point 0, 1. We could plug in another value, maybe 2. We'll say f of 2. So 2 cubed minus 1 over 2 minus 1. So 2 cubed is 8, 8 minus 1, all over 2 minus 1. Well, 2 minus 1 is 1, so 7 over 1. So 7. F of 2 is equal to 7. So we would have the point 2, comma 7 on our graph. Those are XY pairs that match that particular graph. Let's go ahead and use Desmos to do a little bit of graphing. See what happens here. So I could say f of x equals x cubed, so I'm using the shift 6 key, minus 1 divided by, oh nope, I need to select the whole thing, divided by x minus 1. And we get a nice graph there. Looks like a parabola. And if I click over here on that, and then I click on the function, and then I click on the edit, and I click convert to table, one of the really cool things is that it's going to show me a table of some of those values. So at -2, it's the function value is 3, like we're seeing right there. -1, it's -1. I wonder if I think about it, double click there. At 0, it's 1, just like we found earlier, 0, 1. At 2, at 7, ooh, okay, there we go. We've got all kinds of different points going on there. Great. So that's interesting. We've got some different things there. However, I'm looking at that table and I see something that's kind of interesting. At the x value of 1, according to this, my function is undefined. So I'm going to zoom in and I'm going to say, okay, here's an x value of 1. Well, not really. It looks like it's 3 right there. Why is it saying it's undefined? I zoom in closer and closer and closer, and it really looks like it's 3. So let's plug in 1, just like we plugged in those other values, and see what happens. So f of 1 equals 1 cubed minus 1 over 1 minus 1. 1 cubed is 1. 1 minus 1 is 0. So you have 0 over 0. Well, 0 in the numerator is really no big deal, okay? 0 in the numerator is fine. The problem is that 0 in the denominator, okay? Let me just talk about that for a minute, because we are going to deal with zeros in the numerator and denominator a lot. We need to make sure we know what's going on. So 0 in the numerator, it's fine. 0 divided by 5, that's 0. 0 divided by 10, that's 0. What that corresponds to, I have 0 pieces of candy divided by 5. I've got 5 friends. How much candy does each friend get? They each get 0. I've got $0. 10 people I'm distributing it to. How much does each person get? $0. But 0 in the denominator, that doesn't make sense. I have 5 pieces of candy and I have 0 friends. How much does each person get? Well, there's no one. There's no one to get. So if I put 0, then I mean each person gets 0, but there isn't a person to even get a piece of candy. So there's no real world answer or number that corresponds to this division, dividing it into 0 groups. Okay? You can't divide 5 into 0 groups. There's always going to be at least one group. So we say that does not exist. And so as a result, we say that f of 1 does not exist. So even though on Desmos the graph does kind of look like this, they're actually, if they were going to do it right, they would draw a circle in the graph right there. So the graph should look like if you were to exaggerate it, should look something kind of like that. I'll see if that's in the frame here. Oh yeah, we got all the way to that. However, mathematicians are like, yeah, I get it. There's a hole right there, but it's getting closer and closer to a number, isn't it? They said, yeah, it is getting closer and closer to a number. If I look at this graph, it looks like it's getting closer and closer to 3. If I look at it from down here, it looks like the y values are getting closer and closer to 3. So mathematicians came up with a way, a notation of saying, what is the graph getting closer and closer to? And let me show you what that notation looks like. That notation is this. They say the limit of x cubed minus 1 over x minus 1 as x approaches 1 equals, and we look and see based on the graph, as x gets closer to 1, we're marching along here, marching up here, looks like it's approaching 3. As x gets closer this way, the ants go marching closer and closer to that x value of 1, looks like we're approaching a value of 3. So we would say the limit of x cubed minus 1 over x minus 1 as x approaches 1 is equal to 3. Now, the function value at 1 does not exist. The y value isn't there. But the y values are approaching, they are getting closer and closer to 3. So just like I was getting closer and closer to the stool, but I wasn't actually getting there, these x values are getting closer and closer to 3. Okay? Now, that's called the limit, and I'm going to show you how we can manipulate this table to actually see that as well. So I'm going to go over here to the table, and right here, I think about values that are getting closer to 1. So I might put 0 right there. Then I might put 0.9. That's going to give me a y value of 2.71. Then 0.99, 0.999, and then 1. So, and in fact, if I click on those values, we can see 0.271. I'm getting really close. I think the table is a little bit better. If we look at the table values, look at these tables. The values are getting closer and closer to 1, so 0.9, 0.999, 0.999. And then here we have 2.71, 2.9701, 2.997001. If I were to continue this out, we'd end up getting 2.99999 and then 2.9999999 and so on and so forth. It definitely, those y values, those function values, are definitely approaching 3. Okay, I think we can see that. Now at 3, it's a hole. It's empty. But we are approaching 3. This Goddard? He was not in my classroom or Greensword's classroom at the designated time. Okay. Okay. Do you know where he was? Was he like, did he get a schedule change or something? If he needs talking to, then. Okay. All right. We'll send a message. Do we send it to you or Maribel? Okay. All right then. Yep. All right. We're gonna hold that thought there for a second. All right. So we can definitely see that we're approaching a value of 3. Now, I'm going to add some more numbers over here on the other side. 0, 0, 0. And I'm going to think about, what about as I'm approaching it from the right? Okay, so as we see that we're getting closer and closer to 1 from the left, so 0.9, 0.999, 0.99. So what about, let's go with, I'll start way down here, I'll say 2. Here I'll say 1.1, 1.01, 1.001. And we can definitely see the trend going that way as well. Then if you look at it at 2, our y value is 7, but at 1.1, the y value is 3.31. At 1.01, it's 3.03. Then 3.003. We're definitely getting closer and closer to a value of 3 on either side. So in this case, we have absolutely proved via a table that the limit of this function as the x value is getting closer and closer to 1, I'll zoom out so you can kind of see that. So here's the 1 line right here. As we're getting closer and closer to 1, the y values are approaching 3. We really see them kind of all sort of get clumped up there. It's a hole at 3, and Desmos is so detailed it's not going to be able to show us the hole, but we as smarter than Desmos math students know that the function value f of 1 does not exist. But the limit, as x approaches 1, is equal to 3. All right? And in our next lesson, we'll talk about things like, well, what happens if you're approaching it from one side, it's one number. If you're approaching it from the other side, it's a different number. We'll find out that that's a case where the limit doesn't exist, and that's what we're going to talk about in our next lesson. So at this point, we just want to kind of introduce the idea of limits, the idea of approaching, getting closer and closer to a certain value, and how that's different from the actual function value at that point. All right? So that's the beginning of finding limits graphically and numerically. Thanks for watching.